solve a problem on a stepped bar. It is a stepped bar. In stepped bar, we are going to solve a problem. An axial load of 4 into 10 power 5 Newton is applied at 30 degrees Celsius to the rod as shown in figure. An axial load of 4 into 10 power 5 is applied at 30 degrees Celsius to the rod as shown in figure. The temperature is then raised to 60 degree. Calculate the following: assembly of K and F matrix, nodal displacement, stress in each material, reaction at nodal point. Therefore, it is our stepped bar. Two different materials. It is a composite bar, composite stepped bar. Two different materials, aluminum and steel, are combined, and the temperature is raised to from 60 degree to 30 degree. Therefore, we have to find the delta T, change in temperature, also in this problem. And for aluminum, we have given the area, Young's modulus, and this alpha is given the thermal coefficient. Alpha is thermal coefficient. It is given as 23 10 power minus 6 per degree Celsius. And for steel area, Young's modulus is given, and thermal coefficient is also given 20 10 power minus 6 per degree Celsius. And length of aluminum and steel also given, that is 200 mm and 300. Therefore, you have to proceed this problem. In this problem, it's a compared to previous problem, there is a different case in this. There is thermal coefficient is involved, and the temperature rise is also involved. Therefore, we have to find the forces separately for each and every material. First, you take the for element 1. For element 1, first you take the aluminum rod. The length of the aluminum is 200 mm. This is our first element. 1, 2, Q1 and Q2. We know that force vector F equal to K into stiffness matrix into U, displacement. It is the same formula we are going to use to find the stiffness matrix. Therefore, there are two forces involved, F1, F2. What is the K formula? AE by L. 1 minus 1 minus 1 1. U1, U2. It is the formula for first element. We substitute A value, E value, L value of aluminum. Take area. A is 1000. Check the units also. All the values are in mm or meter. Check the values also. E value 0.7 into 10 power 5 Newton per mm square divided by length is 200 mm. The length is also 200. All the values are in mm. Into 1 minus 1 minus 1 1. U1, U2. Two displacements in first element. Is equal to F1, F2. Now you calculate this value.
3.5 into 10 power 5.
3.5 into 10 power 5 is the value. 1 minus 1 minus 1 1. U1, U2 is equal to F1, F2. You take the common term, keep the common term as 10 power 5, multiply 3.5 inside. Therefore, 10 power 5 into 3.5 minus 3.5 minus 3.5, 3.5. U1, U2, which is equal to F1, F2. It is the force vector for the first element. We also mark here A11. This value is A12, A21, A22. These are the vectors, that is matrix for the first element. Stiffness matrix for the first element. Next you take for element 2. The element 2 is steel. The element 2 is steel. Draw the element. Second element. The length of the second element is 300 mm. And mark the node also. Node values 213, Same formula, that is F2, F3, force vectors F2 and F3 is equal to A2, E2 by L for the second element. Stiffness matrix 1 minus 1 minus 1 1, then U2, U3. It is the nodal displacement for second element. Therefore, substitute the value of AEL from the, for steel, A is area 1500, check the values, all the values are in mm. Then Young's modulus 2 into 10 power 5. Then L2, length of the second element is 300. 1 minus 1 minus 1 1. U2, U3 is equal to F2, F3. It is the matrix. You check the value.
10 into 10 power 5.
Check the value.
10 into 10 power 5.
10 into 10 power 5. 1 minus 1 minus 1 1. U2, U3, F2, F3. Now you take the common, keep the common term outside, 10 power 5 outside, multiply 10 inside. 10 minus 10 minus 10, 10. U2, U3 is equal to F2, F3. It is our second element, stiffness matrix, force vector and stiffness matrix. Now you find, after finding the element 1 stiffness matrix and element 2 stiffness matrix, you have to assemble the stiffness matrix. Assembly of K matrix, K stiffness matrix. In our question they are asked, first question is assembly of K stiffness matrix. Therefore, you mark the terms also here A11, A12, A21, A22. Similarly here A22, A23, A32, A33. It is our elements. Now you take the common term. Common term is 10 power 5. First you write A11, A12, A13. First row, first column. Similarly, A21, A22, A23. Similarly, A31, A32, A33. You get 3 cross 3 matrix. A11 is 3.5 minus 3.5. A13 is 0. A21 minus 3.5. Here 3.5. A22 is 3.5 here. A22 is 3.5 and A22 there is another term, another value is here 10. Therefore add both the values. Plus 10. A23 minus 10. Then A31 0. A32 minus 10. A33 10. We get 3 cross 10 matrix. Write the displacements U1, U2, U3 which is equal to F1, F2 and F3. It is the assembly of stiffness matrix. Next you go to find the force vector. Force vector F. You know the formula for first you take the element 1. You take element 1, force vector, you get F1, F2 is equal to EA alpha delta T minus 1, 1. EA alpha delta T minus 1, 1. What is delta T here? Delta T is the change in temperature. Delta T equal to 60 degree raised to 60 degree. Therefore, 60 minus 30, that is 30 degree. It should be in degree Celsius. Please check, it should be in degree Celsius. Its value. You substitute there for first element. For aluminum we are going to solve F1, F2. What is the E value? 0.7 into 10 to the power 5. Area A1 is 1000. Check the values, all values should be in degree Celsius and millimeter. Then alpha 1 is coefficient, thermal coefficient is 23 in 10 to the power minus 6 per degree Celsius. It should be in degree Celsius. Then delta T is 30 into 30 minus 1, 1. To calculate this value,
0.483.
0.483 into 10 power something
By 10 power 5.
into 10 power 5 minus 1, 1. This is the value of this for aluminum. Next. Similarly, you keep the common terms 10 power 5 outside and multiply 0.483 inside. Therefore, F1, F2 is equal to 10 power 5 outside 0.483 minus 0.483 minus 480, then plus 480. You multiply common terms. Similarly, find for element 2. Element 2 is C. We know that A, E and alpha. Therefore, write the formula once again. F2 and F3 is equal to B2, A2, alpha 2, delta T minus 1, 1. So please remember this formula EA alpha delta T. And change in temperature is given, the thermal coefficient they will be. Therefore, you remember this formula to find the force vectors. You substitute the E value 2 into 10 power 5, A value area 1500. Alpha thermal coefficient 20 into 10 power minus 6 per degree Celsius. Delta T already we calculated is 30 degrees Celsius. 30 into minus 1. You multiply
1.08 into 10 power 5.
1.08 into 10 power 5 minus 1, 1. You keep the common term outside, 10 power 5 outside. You multiply 1.08, that is minus 1.08 plus 1.08. This is the value of F2 and F3. Now you go for assembly of this matrix. Go for assembly. In continuing that F1, F2 assembly of force vector F1, F2, we have to assemble the force vector F1, F2. Assembly of force vector. Therefore, F1, F2, F3. It is already we have found this value F1, F2, F2, F3. This is the first value, second value, this is second value and third value. Therefore, we have to add the second value. And there is also a value, load P. Load value P is acting at point 2, at node 2. Therefore, at F2, we have to add the value also. Since there is a tensile force, we have to add the value. Therefore, F1, take 10 power 5 as common. Common value is 10 power 5. 0.483 minus 0.483. At F2, there are two values. Therefore, 0.483 minus 1.08, and also we will add the value of 4, that is 4 into 10 power 5. 4 into 10 power 5. 10 power 5 is common there, therefore directly we add the 4 value here. 4 into 10 power 5, 10 power 5 is common, therefore we add the 4 value, and then 1 point, remaining value is 1.08. Now you add this value, plus 4 minus 1.08 plus 0.483, and you get the value of F2. 1 into 10 power 5 is common, minus 0.483,
3.403.
3.403, 1.0. It is the value of F2. Now we know the assembly of K matrix. Already you have found the value of assembled K matrix. Therefore, you substitute the value of force vector there. That is 1 into 10 power 5. K matrix 3.5 minus 3.5, 0, minus 3.5, 13.5, minus 10, 0, minus 10, 0, 10. Displacements U1, U2, U3 is equal to F1, F2, F3. It is the assembled K matrix. Now you substitute this value F1, F2, F3 here, you get the value 1 into 10 power 5. This same value, right? Same value 3.50 minus 3.5, 13.5 minus 10, 0 minus 10, U1, U2, U3. It is equal to common term, you take 1 into 10 power 5 is common. Write the F1 value 483, 3.403 and 1.6. It is the assembled values. Now you substitute our boundary conditions. We know our boundary conditions. Boundary conditions. Applying boundary conditions. What are the boundary conditions here? At node 1 and 2. You see the diagram at node 1 and 2. It is fixed. Therefore, U1 and U3 is 0. U1, U3 is equal to 0. And we know the force at 2. There will be displacement at second point. Therefore, after substituting these boundary conditions, U1 becomes 0, U3 becomes 0. Since these two values become 0, we can neglect first row, third row, first row, third row, and first column, third column. First row, second row, first row and third row, first column and third column is deleted. Since U1 and U3 is 0. And the common terms, you can see the common terms 1 and 10 power 5, you can also delete the common terms also. Now, we get only the U2 value, that is 13.5 U2 is equal to 3.40. Now, directly we can find the U2 value by dividing 3.403 divided by 13.5. You get the value. What is the value of U2?
0.2521.
0.2521. It is the value of U2.
Mm.
It is the value of. It is our result. U1, U3 is 0. U2 is 0.252 mm. It is our result. Next, you have to find the force vectors, that is reaction forces. Before reaction force, you have to find the stress values. You have to find the stress values at element 1 and 2. Then you know the stress formula. What is stress formula? If there is Young's modulus, if there is any delta change in temperature and the thermal coefficient is there, you have to apply the stress formula as sigma equal to E into du by dx minus E alpha delta T. It is the formula. When you apply the thermal coefficient and the change in temperature, the stress formula becomes like this. Therefore, for element 1, you write the stress formula sigma 1 equal to E1 U2 minus U1. It is the change in displacement at element 1 and into dx. Dx is length 1, length of the first element. Then E1 alpha 1 delta. You substitute all the values, you know all the values. What is E1? E1 is 0.7 into 10 power 5. 0.7 into 10 power 5. U2 minus U1, U2 value you know 0.252 minus U1 value is 0. And the length of the first element is L1 is 200 mm. It is 200 minus 0.7 into 10 power 5. Alpha 1 value, that is alpha 1 is thermal coefficient of first element, 23 into 10 power minus 6. You also check the units, whether all the units are in that is the same unit. Then delta T is 30 degrees Celsius. When now you solve this values, you get the value of stress value of sigma 1. It comes around
39.935
39.93 Newton per
millimeters.
mm square. It is the value of sigma 1. Similarly, you find the value of sigma 2. Similarly, find the value for element 2. Sigma 2 equal to E2 into U2 minus
U3 minus U2.
U3 minus U2. L2 minus E2 alpha 2 delta T. Now substitute all the values here. E2 is 2 into 10 power 5. U3 value is 0 minus 0.252 divided by length is 300. 2 into 10 power 5. Alpha 2 is
12 into
10 power minus 6. 10 power minus 6 into change in temperature is 30 degrees Celsius. Now you solve this, you get the value of sigma 2
minus 240.066.
Newton per meter square. Since it is minus, it is called as a compressive stress. And if it is positive, it is called as a tensile. Tensile stress and compressive stress. Since there in first element there is elongation takes place, therefore tensile stress takes place, and there is in the element 2 the compression takes place, and therefore compressive stress takes place. Next, we have to find the reaction forces. That is R vector we have to find. The formula to find the R vector is K matrix, the same, U displacement minus force vector. You have to minus the force vector to check the reaction components. Whether the value, force value is correct or not, you have to check the values. Therefore, we can check the reaction forces R1, R2, R3. There are 3 node points. And the K matrix, we know K matrix is 1 into 10 power 5, 3.5 minus 3.5, 0, minus 3.5 minus 13.5 minus 10, 0, minus 10 and 10. And displacements, U1 is 0, U2 we got the value 0.252 and U3 is 0. Minus the force vector, the same, 1 into 10 power 5 you take common, F1, F2, F3 value. What is F1 value? 0.483 and F2 value 3.403 and F3 value 1.08. Now you cross multiply the matrix. second row into this column and third row into this column. You get the values. That is R1, R2, R3. 1 into 10 power 5 is common.
Minus
The value
0.8823.
3.5 into 0, 0 minus 3.5 into 0.25.
Minus 0.8843. 8823.
0.88.
23.
8823. Okay, it is the first value. Next, the second row into column.
3.
Minus 3.5 into 0 becomes 0. 13.5 into 0.25.
3.403.
403. Minus 10 into becomes 0. Next, third row into column. Minus 10 into 2.52.
Minus 2.521.
52. Next, the remaining values you write. Minus 1 into 10 power 5. Minus 483. 3.403 and 1.0. It is the matrix in the sign minus sign. Therefore, directly we can minus this value and we get the total value. That is R1, R2, R3. 10 power 5, 1 and 10 power 5 is common. Minus 0.8823, then plus 0.483.
Minus 0.3993.
You get the value. Minus 0.8823, then here there is a minus, therefore positive 0.483. You get minus 0.399. Next, 3.403 minus 3.403 becomes 0. Then minus 2.52 minus 1.08 you get
Minus 3.601.
minus 3.0. Now we can see the
601.
3.601.
601.
Okay. Now we check the value, you can get the value. Total load we have applied is 4 into 10 power 5 Newton. Therefore, it is nearer to the value. You can see the value is nearer to the 4. Therefore, when you add this value, you know now you know R1, R2, R3 value. When you add the values, you get minus 4, around 4. Therefore, it is verified. Our reaction forces is getting minus, therefore it is in opposite side. Reaction forces are different in opposite direction. We have verified. Therefore, the reaction forces are verified. We will be getting the reaction force minus side. Therefore, it will be in the opposite direction. Reaction forces R1, R2, R3 is 4 into minus 4 into 10 power 5. Therefore, it is verified. It is our result. That result is nothing but you have to assemble the K matrix, then you have to assemble the force vector, then you have to find the elemental stresses sigma 1 and sigma 2, then you have to get the reaction forces and you have to check whether the reaction forces are correct or not. Thank you.